After having done this, let me now state that what is my lambda ij. So, lambda ij, if you note, your lambda ij is nothing but matrix element of this quantity with chi j1, f of 1, chi I1, correct? And lambda ij prime is nothing but the same thing, but with chi j prime, correct? So, that is the reason lambda will change to lambda prime, because the lambda depends on chi. It is a matrix element of Fock operator. It is very easy to see this. If you just make a multiplication, because they are orthonormal, only one term will survive. So, of course, you can say k, kj, ij, whatever, that is a dummy index, that is specific index. So, the point is that this is a matrix of Fock operator in a basis. This is also a matrix of the Fock operator in the new basis, which is unitary transform. Now, we know from the matrix eigenvalue equation that if I choose a proper unitary transformation, any matrix can be diagonalized. Now, this is why I am doing unitary transformation. Now, you understand immediately? So, without any further ado, I would now say that choose a matrix U, because I have several unitary transformations. So, I will say choose U, this is my choice now, such that lambda is diagonal. Okay? So, something like this, U dagger lambda U is some epsilon, where epsilon is diagonal matrix. So, this is a diagonal matrix. You can always write U lambda U dagger, does not matter, whichever way you want to write. This is always possible, because this is a matrix, and not only that, this is a Hermitian matrix. I must also make sure that you understand this is a Hermitian matrix. If you take a dagger of this, you will see that this chi I, star will come here, and this will become lambda gi. So, this will also flip, and the Fock operator by itself is Hermitian. I should have said this before, that if you look at the Fock operator, the F operator is also Hermitian. I think I must mention this point. Once again, I hope you are able to see this. H is Hermitian, right? This is my JJ. JJ is also Hermitian, because if I take adjoint of this, what will happen? This chi j will come here, this chi j star will go here. This is already a Hermitian operator. Same way exchange, P12 is a Hermitian operator. So, entire Fock operator is Hermitian. This is nothing but a matrix element in an orthonormal basis of a Hermitian operator, and hence this is also a Hermitian matrix. This original lambda is a Hermitian matrix. Please note that there is a difference. This is a Hermitian operator, this is a Hermitian matrix, because this is a matrix, these are numbers. Whenever you have numbers, they can't be an operator. Of course, number can be an operator, but in this case, these numbers can be arranged in the row and column. Okay? So, that is the reason I said it is convenient sometimes to look at Ji, because then you will see that the J is on the left, I is on the right, but it does not matter, however you look at it. The point is that this lambda is a Hermitian matrix, because Fock operator is Hermitian. Since it is a Hermitian matrix, I can always find a unitary transformation such that the matrix can be diagonal. So, now I am saying that let us choose a U such that lambda is diagonal, and then rewrite this Hartree-Fock equation. Quite clearly, now this is my lambda prime. So, lambda prime is now diagonal. So, lambda prime ij is now epsilon, let us say epsilon I delta ij, right? That is the meaning of diagonal. So, this is a diagonal matrix. So, the new lambda prime in the new basis will become diagonal after transformation. Note that I am transforming everything through chi, but the lambda's transformation has to happen in this manner, because lambda has one chi on the left, one chi on the right. So both of them have to be transformed, and quite clearly I can always choose a transformation such that this will become diagonal. Now quite clearly if you say that any unitary transformation I take, I can't show that it is diagonal. Any arbitrary transformation, no, I can't show. So now I am actually deviating from here. I am saying this is a matrix, let's choose U, that is very important, such that it is diagonal. So this is my choice. The question is, how do you choose U? Now that is a point where you are actually saying, how do you diagonalize a matrix? Now that is something that I will not bother right now. Why do I choose? So then there will be a question, because I am following variation method. My mathematics gave me a matrix. So if you choose, that's another constraint. I did not know my mathematics, what it will lead to. I started variation, psi A psi. I only had a constraint that chi should be orthonormal. And lo and behold, I got this equation. Okay, I didn't know what equation I will get. Once I have got this equation, now I am trying to analyze how can I make it diagonal. And then I find that this is a Hermitian matrix. So Hermitian matrix can be diagonalized by unitary transformation. But then I have to worry about what happens to the rest of the equation through the unitary transformation. So one thing I understood, that the f remains invariant. Okay, and then I can write this rest of the equation is just f. So this becomes chi I prime. These spin orbitals are now transformed spin orbitals, of course, but that I don't care. Okay, so eventually I can then write f of 1 as some new chi I prime 1 equal to epsilon y chi I prime 1. You understand? Because now your lambda prime in the new basis is diagonal by my choice, and that choice will be dictated by how to diagonalize a matrix. So that is the part I am not going to discuss here. That's the mathematics. All of you should know by now how to diagonalize a Hermitian matrix. How do you get this U? Provided I get U, what I am now suggesting is that the new spin orbitals can be chosen such that they are eigenfunctions of the Fock operator. New Fock operator is same as old Fock operator, so I am not writing F prime. Okay, is it clear? And now I have got a canonical form without any problem, which is a nice eigenvalue equation, which is what you wanted all the time and which is what you are used to. So I will give the interpretation to what is epsilon I. You already know these are orbital energies, these are the orbitals and everything. Okay, but I will give the interpretation. Today what we have done is that we have started from the non-canonical Hartree-Fock equation, which we have derived last time. So we have started from non-canonical Hartree-Fock equation, which is a general, this is the form that we derive from the variation method. So this I am not going to worry. It's a non-canonical Hartree-Fock equation. So this is something that I have derived from the variation method. Okay, and the form of that was f of chi I is sum over j epsilon I j chi j. I am not writing f of 1 explicitly, it is an operator equation, so it does not matter. So I have started from this non-canonical equation. Then I discussed the effect of unitary transformation on this equation. Okay, I noted the fact that the f is Hermitian, that is the first thing. And hence, sorry, not epsilon, this was lambda, does not matter. And lambda is a Hermitian matrix. This is something that I notice and I preserve it in any basis. It does not matter what is the basis, as long as this equation is satisfied, whether you do unitary transformation or not. This is a Hermitian operator, so this is a Hermitian operator, and the lambda is a Hermitian matrix, correct? Now I do a unitary transformation. So unitary transformation leaves f invariant. So that is the next thing we showed. Unitary transformation also leaves the spin orbitals orthonormal. retains the orthonormality of the spin orbital. In general, any basis, if you have any basis, you can do unitary transformation. So that also we saw. Then what we said, that after having known all this, we are now merely saying choose a transformation such that lambda is diagonal. This is my choice. So please note that by an arbitrary unitary transformation, I cannot make lambda diagonal. So then you will get arbitrary lambda prime. But now I can choose such that it is diagonal. So my Hartree-Fock equation then will become canonical, and it will become f of chi I prime in the new basis as epsilon I chi I prime. The same Hartree-Fock equation which I started now has a canonical form simply because I am able to make this matrix diagonal by unitary transformation, by suitable unitary transformation. I could have right away said that this is a Hermitian matrix, so simply diagonalize this. But then you would have asked question, if I diagonalize this, what happens to the rest of the equations because of unitary transformation? So that is the reason I had to show elaborately that the F operator remains invariant, the unitary, the spin orbitals remain orthonormal, so I can do it, I have no problem. Otherwise it was very easy to see. If I just wanted to make it diagonal, yes, that's what we know, just do unitary transformation. But it might have created havoc on the rest of the equation. Then I have to re-understand the equation itself. So the point that I am trying to show that the equation does not change because the Fock operator remains Hermitian. And that is a very important thing, and I get a canonical Hartree-Fock equation. So this is canonical Hartree-Fock equation. And all my interpretations become much easier in the canonical form. But note, however, and I will show later, that the total energy of the system remains same whether you use non-canonical or canonical. The only thing, however, that has changed is the spin orbitals. So spin orbitals are different, but eventually I will also show that the wave function remains the same, energy will remain the same. I will also have to study what happens to the wave function, because wave function was in the old spin orbitals. Now I have new spin orbitals. I must understand, has the spin orbital function changed? And I will actually show that that does not change. Hence energy also does not change, total Hartree-Fock energy. So everything remains same. Orbitals, however, change. These epsilon i's are called orbital energies. So they have a meaning, and this has no parallel for the non-canonical part, because non-canonical, it is a matrix, so I can't say that one number for one orbital. So it has no parallel. So the orbital energy is a very special term, remember, which is used only for canonical Hartree-Fock equation. If I tell you this is orbital energy, that means we have solved canonical Hartree-Fock equation. Otherwise, orbital energy has no meaning. And lot of interesting things will be done, interpretation, physical interpretation will be done through the canonical Hartree-Fock equation. Okay? So let's look at what happens to the wave function first. So let's look at the wave function in the new spin orbitals now. So if you remember the wave function, now I call it Hartree-Fock wave function. In the original basis, this was chi 1, whatever, chi 1, 2, etc., chi 1 n, chi 2, 1, chi 2, 2, chi 2 n, and so on. So it's a determinant, chi n 1, chi n n. Okay? When I do the new Hartree-Fock, what will happen is that each of these chi i's will now become chi I prime, which is related to U by the matrix transformation of U. So one can write this matrix itself. How will this matrix look like? Let's say this psi Hartree-Fock is determinant of A. You understand? And A is this matrix. So I am just rewriting this. This psi Hartree-Fock is a determinant of a matrix. We have never seen it this way. Of course, there is a 1 by square root n factorial. So let's not forget that. Okay, that's fine. This is not going to change anyway. So, I am worried about what happens to the determinant of A when the basis is changed. When the basis becomes chi I prime, it will be very easy to show that the new matrix A prime will be nothing but A times U. Please do this exercise, because each of these chi I, when I write as a sum over U chi j, you can very easily separate these into the product of two matrices A and U, which would mean that the new psi Hartree-Fock prime, please check this yourself, psi Hartree-Fock prime, which will be determinant of AU, which is nothing but determinant of A times determinant of U. What is the determinant of U? It is a phase not 1, exponential I5. Please do not say 1. 1 is an incomplete answer, right answer, but only an incomplete answer. Okay? I hope all of you will be able to find determinant of U. We have done that in various courses. From the very fact that U dagger equal to identity, you should be able to do this. Right? Determinant of whole thing, determinant of U into determinant of U dagger. Determinant of U dagger is very easy, determinant of U star. Right? What is determinant of U dagger? It is U star. So, this determinant is U star is equal to 1. Remember, determinant is a number. So, when I take determinant on the both sides, this is 1, this is determinant of U, determinant of U dagger. Okay, determinant of U dagger is nothing but U star determinant. So, it's a number, it's a number. So, let us say x into x star equal to 1. What is the value of x? Exponential I5. Okay, not because in the complex plane. So, determinant of U is nothing but exponential I5. So, that means my psi Hartree-Fock prime is nothing but determinant of A, which is psi Hartree-Fock, times a phase factor. And all of us know that the phase factor does not change the wave function. I hope you remember the basic quantum mechanics, that I can multiply my wave function by any number or any complex number like exponential I5, no property will change. So, the energy obviously will not change. I do not have to prove you now, because Hartree-Fock energy is nothing but psi HF, H, psi HF. So, psi HF on the left, psi HF on the right. Psi HF on the left will give you, psi HF prime on the left will give you exponential minus I5, and on the right it will be exponential plus I5, it will become 1, correct. So, it is very easy to show that the energy also remains invariant. So, because of this now, E Hartree-Fock prime is psi Hartree-Fock prime H psi Hartree-Fock prime, and is same as psi Hartree-Fock H psi Hartree-Fock. Okay? Because these two together, these are related by only a phase factor. So, only phase factor on the left and on the right. So, the left one will produce you exponential minus I5 multiplies by exponential plus I5, it gives 1. In fact, that is the reason no properties change. So, you can always multiply anything by phase factor. Of course, phase factor also leaves the wave function normalized. That is also important. That is the reason I am not dividing by anything. If I on the other hand multiply by 2, then what will happen? This will actually become 4 times, 2 into 2, because it is no longer normalized. Then I have to also divide by psi Hartree-Fock prime nor, which is again 4. So, I would have got that 4 cancel. That is the physics. But here I do not have to do, because this remains normalized and I see that the energy remains invariant. So, the Hartree-Fock energy, Hartree-Fock wave function, they all remain invariant. So, the only thing that is changing, however, are the spin orbitals. So, spin orbitals are not sacrosanct. Canonical spin orbitals are one, non-canonical are something else, and I can actually generate several spin orbitals, set of spin orbitals. And that is the reason in the molecule, you must have already read that, let us say methane molecule, I have spin orbitals which are delocalized over the orbital, over the entire molecule. They are called delocalized orbitals. Forget about spin, delocalized orbital. I can then make a unitary transformation such that the spin orbitals are in only one direction of the bond, carbon-hydrogen. You must have seen directional properties. So, they become localized spin orbitals. So, delocalized versus localized spin orbitals. Actually, it turns out that these delocalized ones are the canonical ones. That's a later part. So all the canonical orbitals are actually delocalized. So it's very hard. That is the reason when the molecular orbital theory, we start with this orbital, they are all delocalized. It becomes more and more difficult to do simple chemistry sometimes. But then this is the way to go forward. Olden days when people used to do valence bond, they were all localized. We know that these are the bond, these are atomic orbital, they are all localized. But then they did not have orthogonality property, lots of problems were there. Here everything is preserved. So when the high performance computers came, this became the method. Even though sometimes the chemistry gets a little fuzzy, because I can always get back the chemistry later. So this becomes an easy way to do the canonical Hartree-Fock equation. So with this, I think we will not worry about the non-canonical Hartree-Fock. From now on, whatever is the Hartree-Fock is the canonical Hartree-Fock. Okay, so whatever in the future that we will discuss is only canonical Hartree-Fock equation. So I hope all of you realize that they are identical. There is no difference, and hence, since we are only going to discuss canonical Hartree-Fock equation, I am not going to write this prime anymore. So the prime and unprime was my creation, right? So my canonical Hartree-Fock will be chi I, because there is nothing called the old chi I now. Is it okay? This is not any cheating. Huh? It is just that my symbol I am changing. Why to write prime all the time? So I will say drop the prime, and we will start with f chi I equal to epsilon I chi I. And we assume that these are the canonical orbitals from the rest part of the discussion that we will start. So we will actually look at the physical interpretation of canonical Hartree-Fock equation. What is the, how can I write an expression for orbital energy? What is the interpretation of orbital energy, in particularly in terms of Koopman's theorem, that the negative orbital energy is ionization potential and or electron affinity, all that will come. So basically interpretation of the orbital energies and some more interesting aspects of the Hartree-Fock theory before we go do the same equations in spin adapted form. Remember, we have written everything in terms of spin so far. You may like to know, can I do the spin integration? How to do it? It's a trivial exercise. So I will just spin integrate the same equation very quickly. For a specific system, let's say again closed shell. We have already discussed what is closed shell. All W occupied orbitals, we will actually show how to do that, and then we will have a Hartree-Fock equation only in spatial orbitals. Now it is in spin orbitals, Hartree-Fock in spatial orbitals, then we will see how to solve this. The solution is not so easy. So how do I solve? But before that I will do the spin integration, and how do I solve it, and that is where the metrics and lots of things will come. Basis set that you have heard, that will all come in the solution. Right now there is nothing called basis set. The basis set will come only when I try to solve the spatial orbital Hartree-Fock equation. Okay, so that will be the way, and then I will go over beyond Hartree-Fock later. All right, I will close the lecture today.